In this video, we are going to continue looking at graphing polar equations. So far we've looked at converting polar coordinates to rectangular coordinates and vice versa. And we've been looking at converting polar equations to rectangular equations and vice versa. We looked at some general shapes of what some of our polar equations would look like and their graphs. Before we jump into reviewing that really quickly, let's review what we've learned about converting. So recall that x is equal to r cosine theta. We saw that y was equal to r sine theta. And we saw that r squared is equal to x squared plus y squared. So in our last video, we looked at graphing some polar equations that gave us the shapes of circles. And so we can recognize that we're going to get a graph of a circle if we have an equation in the form of r equals a, where a is some number. If it was r equals a, then we have a center of our circle is at the origin, 0, 0, and our radius is a. We also saw that there were some different forms of getting circles. And so if we had the form of r is equal to a plus or minus a cosine theta, then we saw that we had a circle, but our center was going to be a divided by 2, 0, and our radius was in the form of the absolute value of a divided by 2. We also saw that we had a circle in the form of r is equal to a plus or minus a sine theta. If it was in this form, then we could see that the center was at the point 0, a divided by 2, and our radius, again, is the absolute value of a divided by 2. Then we looked at graphing some polar equations, which gave us back lines. And so if we were to have a line, a graph that looked like a line, the following forms were theta was equal to some real number, let's call it b. Or we could have the form of r sine theta equals some number, let's call it b. If this was the case, then we had a horizontal line at y equals b. If we had the form of r cosine theta equals some number b, then we had a vertical line at x equals that number b. And then lastly, we looked at graphing cardioids. So cardioids gave us kind of an heart shape graph. And so if we had a cardioid, we would have the following equation. So those cardioids, they were in the form of r is equal to a plus or minus a cosine theta, or we had r is equal to a plus or minus a sine theta. These values are where a was greater than 0, and our graph crossed through the pole. So now let's look at some other types of equations that you may see while you're graphing these polar equations. And so the next one is called a Limacons curve. I don't know if I'm pronouncing that right, so I apologize if I'm not. So in front of S is the definition of a Limacons curve, and this Limacons curve is without an inner loop. So if we're going to get a graph of the Limacons curve without an inner loop, the Limacons curve are characterized by the following equations, where we have A is equal to, or R is equal to A plus B cosine theta, R is equal to A minus B cosine theta, R is equal to A plus B sine theta, or R is equal to A minus B sine theta. In this case, that coefficient A is greater than B, which is greater than 0. The graph of the Limacons without an inner loop does not pass through the pole. So let's look at the following equation. We have the equation in front of us that R is equal to 2 plus sine theta. So notice here that our A value is 2. Our B value, that coefficient in front of sine, is 1. And our A value, 2, is greater than 1. So A is greater than B. So this is in the form of a Limacons curve without a loop. And so we talked about looking at symmetry across either the polar axis, theta equals pi half, or the pole, and testing that. And we could test it to help us get some extra points on the graph. So maybe let's just review doing that really quickly to see if this is symmetrical. These tests that we're going to try, if it doesn't hold true, the test doesn't necessarily mean that it's not symmetrical. And so we talked about looking at if it's symmetrical across the polar axis. So the polar axis, what we would do is we would plug in negative theta in for theta. So if we do that, we get R is equal to 2 plus sine of negative theta. If the equation R remains unchanged, then it would be symmetrical across the polar axis. I noticed that sine of negative theta is the same thing as negative sine theta. So rewriting this, I see that my equation is not the same. So this doesn't tell me that it's symmetrical across the polar axis. It's possible to still be symmetrical across that polar axis, but this test doesn't show me that it is. So we could also test to see if it's symmetrical across the line theta equals pi halves. So if it's symmetrical across this line, theta equals pi halves, then we're going to replace theta with pi minus theta. And so let's do that. Doing that, we would get R is equal to 2 plus sine. So replacing theta with pi minus theta. What we want to see is this equation remain unchanged. So R is equal to 2 plus, so I have a difference of 2 angles for my sine of theta minus pi minus theta. I can use my difference of angles for sine. So this would give me sine of pi, cosine of theta, same sign, so minus sine of theta, cosine of pi. So let's simplify this down a little bit. So we have R is equal to 2 plus, well, sine of pi, that's equal to -1, cosine theta, minus sine theta, and cosine of pi is equal to -1. And so we have -1 times this sine of theta. So R is equal to, and I made a mistake, sine of pi is 0. And so R is equal to 2 plus, because minus a negative, sine of theta. And so I noticed that this is the same thing as my original equation, r equals 2 sine of theta. So this remains unchanged. So we know that it's symmetrical across the line, theta equals pi halves. So now we can check to see if it's symmetrical across the pole. So it's symmetrical across the pole. There's two different tests that we can use. So we can replace r with negative r. I notice right away, if I replace r with negative r, I'm going to get a different equation. So replacing r with negative r, but let me just show it really quick, is equal to 2 plus sine theta. To get r positive, we would multiply both sides by -1. And doing that, we would get r equals, well, I'd have to distribute the -1 on the right-hand side. So I would get -2 minus sine theta. So this does not equal my original equation. So this doesn't tell me that it's symmetrical across the pole or not. The other way is to look at it by replacing theta with theta plus pi. So if I replace theta with theta plus pi, we have r is equal to 2 plus sine of theta plus pi. So I have a sum of two angles, and I could rewrite this using the sum of two angles for sine. So I have 2 plus, so this would give me sine of theta, cosine of pi, same sign, plus sine of pi, cosine of theta. So r is equal to 2 plus, well, cosine of pi is -1. So -1 times that sine of theta, this is going to be minus sine theta. Sine of pi is 0. So 0 times cosine of theta is 0. So I notice that this is not the original equation. So again, this test does not tell me that it's symmetrical across the pole or not. So from our test, we know that this is symmetrical across the line pi halves. So now let's look at plotting a couple points and getting that graph. So in front of us is our equation again, r is equal to 2 plus sine theta. If we have a point, r theta, because we saw that it was symmetrical across that line, theta equals pi halves. And then we also know that r comma pi minus theta is also a point. And so let's start plotting points. And so let's choose values of theta that we know. And so let's look at theta equal to 0 first. If we plug in 0 for theta, sine of theta I know is 0. And so r is equal to 2. Well, pi minus 0 is pi. And so I know that here, that I would still have 2, but pi minus 0, again, I just said is pi. So we have a point also at 2 pi. Let's look at another value. So what if we put in pi 6? So if we plug in pi 6, I know that that sine of pi 6 is 1/2. And so I have 2 plus 1/2, or that gives me 2.5. So if I have pi minus pi 6, this would give me 5 pi 6. And I notice I'd also get that r value of 2.5. Let's plug in pi fourths. If we plug in pi fourths, we have root 2 over 2. Sine of pi fourths is root 2 over 2 plus 2. And so that gives me 2 plus root 2 over 2. So let's plug that into a calculator and figure out approximately what that is, so it will help us graph it better. So root 2 over 2 is approximately 0.7, and so we would have the point here, 2.7 approximately. And so pi minus pi fourths, this would give us 3 pi fourths. Now let's look at plugging in pi thirds. So pi thirds, I know sine of pi thirds is root 3 over 2. And so square root of 3 divided by 2, this gives us approximately 0.9. And so that would give me approximately 2.9. If I look at pi minus pi thirds, that would give me 2 pi thirds. So let's look at a couple other points. Or actually, let's plot what we have so far. Let me pull up a polar graph, graphing paper to help us graph this. So I have some polar graphing paper in front of us. And so let's plot what we have so far. And so we have a point when r theta is 0, r is 2. So we have some point here. When r is pi, so going theta is pi, theta is pi, we get that r is also 2. When we have pi 6, which is 30 degrees, we have 2.5. So about right here. So at 150 degrees or 5 pi 6, we also have 2.5. At pi fourths, which is 45 degrees, we have approximately 2.7. So that's about 135 degrees. We also have 2.7. At 2 pi thirds or pi thirds, which is 60 degrees, we have 2.9. And 120 degrees, we also have 2.9. Let's see what's happening at pi halves. So at pi halves, sine of pi halves is 1. And so I have 2 plus 1. That would give me a value of 3. Plotted my R value wrong for the first over here. So let's see about going underneath the polar axis or in that third and fourth quadrant. So let's pick a couple of values over here. Let me just put them in, since we have it here, into degrees. So 210 degrees, that is a reference angle of 30 degrees. I know that sine is negative in that third quadrant. So that's going to be -1/2. And so 2 plus -1/2, that would give me a 1.5. Okay. So knowing that I have 1.5 here, it's going to be right here. Symmetrical across this line. So I'm also going to have 1.5 here. So let's look at 225 degrees. So at 225 degrees, I know that I'm going to have sine of 225 degrees is negative root 2 over 2. So if I have 2 minus approximately 0.7, this gives me 1.3 approximately. So at 225, I have approximately 1.3. Symmetrical across that line. Let's see what we're getting at 270 degrees. So I know that sine of 270 degrees is -1. And so r is equal to 2 minus 1, which would give me back 1. So there's what our Limacons curve looks like. And so now let's look at the definition or theorem about these Leminscates curves. I think actually I already did that, didn't I? Yep. So if we have on the form, again, of R equals A plus or minus B cosine theta, or R equals A plus or minus B sine theta, where our coefficient A is bigger than our coefficient of B, then it's going to be a Leminscates curve without an inner loop. So now let's look at another form where these Leminscates curve has this inner loop. So in front of us is the definition of a Leminscates with an inner loop. A Leminscates with an inner loop are characterized by the equations in the form of R equals A plus or minus B cosine theta, or R is equal to A plus or minus B sine theta. In this case, our coefficient of B is greater than our coefficient of A, which has to be greater than 0. In this case, the graph of the Leminscates with an inner loop passes through the pole twice. So let's look at the equation R equals 2 plus 4 cosine theta. So I notice my coefficient of A, which is 2, is smaller than my coefficient of B, which is 4. So this tells me I'm going to get a Leminscates curve with an inner loop, and it's going to cross through the pole twice. And so we can test for symmetry if we would like, and use that fact if it's symmetrical, that we have these additional points. And so again, we can test to see if it's symmetrical to the polar axis. So if we replace theta with negative theta and it remains unchanged, which I can see that it is, R is equal to 2 plus 4 cosine of negative theta. Since cosine is an even function, I know that cosine of negative theta is equal to cosine of theta. So rewriting this, I get R is equal to 2 plus 4 cosine theta. So symmetrical with that polar axis. So we can also test to see if it's symmetrical across that line. Theta equals pi halves. We could test this by plugging in pi minus theta for theta. So doing that, let's rewrite this. R is equal to 2 plus 4. I have a difference of 2 angles for cosine. And so let's look at the formula for the difference of 2 angles for cosine. So we would get cosine of pi, cosine of theta, opposite sign, plus sine pi, sine theta. So we have R is equal to 2 plus 4 times that quantity. Well, cosine of pi is negative 1. And so I would have negative cosine theta. Sine of pi is 0. So that sine pi times sine theta, that goes away. I notice that R equals 2 plus 4 times negative cosine theta doesn't give me back the original. So it's not symmetrical across that line. Theta equals pi halves. The other axis of symmetry, or not axis of symmetry, symmetry across the pole. There was 2 different things that we could do. We could plug in negative R for R, which I noticed would change that formula or our equation. So that is not symmetrical, or it doesn't tell us it's symmetrical across the pole. Or we can plug in theta plus pi. So let's try that one. So if we plug in theta plus pi for theta, we would have R is equal to 2 plus 4 cosine of theta plus pi. So this is the sum of 2 angles. Using the sum of 2 angles for cosine, we would have 2 plus 4 times the quantity cosine of theta, cosine of pi, opposite sign, minus sine theta sine pi. Well, cosine of pi is -1. Sine of pi, again, is 0. And so I see that I get not the same thing. I would have r is equal to 2 minus, because cosine again of pi is -1. So we have negative cosine theta times 4. So that's minus 4 cosine theta. So we see that it's symmetrical across the pole or polar axis, not the pole. It's possible that it's symmetrical across pi halves, theta equals pi halves in the pole, because our test for symmetry doesn't necessarily tell us that it's not symmetrical. It just tells us if it is symmetrical, if the tests hold true. So let's look at plotting some points and graphing this. And so let me pull up some polar paper and let's plot some points. So we have our equation in front of us. We have our polar graphing paper in front of us. Let's plot some values. So we're given, again, r theta, because it was symmetrical across the polar axis. If r theta was a point, then r negative theta is also a point. So let's choose values for theta that we know. So at 0, if I have 0, then I have cosine of 0 is 1 times the 4 in front of it. So that's 4 plus the 2, that would give me 6. Well, that doesn't really change anything here, so 6, 0. If I look at 30 degrees, which is the same thing as pi 6, well, I know cosine of 30 degrees is root 2 over 2. So I'm going to have here 2 plus 4 times, not root 2 over 2, root 3 over 2. So plugging that into the calculator to get me an approximate value for r, I have 2 plus, well, that 2 in the denominator goes into 4 twice, so 2 plus 2 root 3, which gives me approximately 5.5. So let's just write it over here. So 5.5, and then it's negative pi 6, or negative 30 degrees, or another way to say that is 330 degrees. So now let's plug in 45 degrees, or pi force. So I know that's root 2 over 2, so that would give me 2 plus 4 times root 2 over 2. 2 goes into 4 twice, so that's the same thing as 2 plus 2 square roots of 2. That gives us approximately 4.8. So a reflection across that polar axis is going to be the same thing as 315 degrees. Let's look at 60 degrees, or pi thirds. I know cosine of pi thirds is 1/2. And so I have 4 times 1/2 is 2, and then that 2 plus the 2 gives me 4. So we have 4 here, and that would be the same thing reflected across that polar axis as 300 degrees. So let's see what we have so far with those points. And so we have a point at theta 0, we have r is 6. When theta is pi 6, or 30 degrees, we got 5.5, which was the same thing as 330, we had 5.5. At pi force, or 45 degrees, we had 4.8, which was the same thing, a reflection across that polar axis is 315 degrees, we have 4.8. At 300 degrees, or pi thirds 60 degrees, we had 4. 60 degrees, we had 4. Here. At 300 degrees, we also had 4. So let's do a couple more points. Let's see what's happening at 90 degrees. So 90 degrees, Cosine of 90 degrees is 0. So we have 2 plus 0, which is 2. A reflection across that axis would give us 270 degrees. We also have 2. So let's look at, how about 120 degrees? So 120 degrees, so the reference angle is 60 degrees, but I'm in the second quadrant, cosine is negative. Cosine of 60 degrees is 1/2, but it's negative. So that's negative 1/2 times 4 is negative 2, plus that 2 is 0. So a front reflection across that polar axis, so 120 degrees is negative 120 degrees, negative 120 degrees is 240 degrees. I also have 0. At 135 degrees, cosine is negative, so I have 2 minus 2 square roots of 2. So that is going to give me approximately negative 0.8. So at the reflection across that, what kind of looks like the x-axis would be 225 degrees. I also have negative 0.8. And so at 150 degrees, that's going to give me, for cosine of 150 degrees, that's negative root 3 over 2 times 4. So I have 2 minus 2 root 3, which gives us approximately negative 1.5. So a reflection of 150 degrees would get me to 210 degrees, which is also negative 1.5. So let's plot those extra points that we just got. And so we have a point 135 degrees. So rotate 135 degrees. I have negative 0.8. So remember that goes across the pole in the opposite direction because our R value is negative. So we have negative 0.8 here. And then at 225 degrees, we also have negative 0.8. And then at 100, oh, that was 135 degrees. Did I do that right? 135. Yep. 225. It's on the wrong line. Okay, so 150 degrees, we have negative 1.5. So rotate 150 degrees, we're going to go across the axes, and we got approximately 1.5. Doing the same thing, 210 degrees across, because it's negative 1.5. Let's also see what we get at 180 degrees. So 180 degrees, I know my cosine value is negative, so I have 2 plus negative 4, which is negative 2. So at 180 degrees, I'm going to go across to 2. So let's look at the graph of this. off a little bit. Which one was the 0.8? That was the 225. 0.8. Looks like this. So it looks similar to this. And let's just pull that up on Desmos and show that we get the same thing approximately. Okay, so looking at what we got at Desmos, you can see the following picture, which is similar to what we got. And so that is a Limacons curve where we have this inner loop in here. So there's other shapes that we can get, and let me pull up what those can be. So we can get what are called roses or a rose. So in front of us is a definition of a rose. A rose curves are characterized by the equations of the form r equals a cosine of n theta, or r is equal to a sine of n theta, where a value or coefficient of a can't be 0. And they will have graphs that are rose shaped. If n does not equal 0, is even, then we say that the rose will have 2 times n petals. So knowing how many petals we have is going to be helpful to know what the graph looks like. If n does not equal plus or minus 1 is odd, then the rose has n petals. And so in front of us, we have the equation r equals 2 sine of 3 theta. So I notice that my n value is 3. And since 3 is odd, this tells me I'm going to have 3 petals. So let's look at this in the graph. So let's test for symmetry again. So if it's symmetrical across the polar axis, we would plug in negative theta for theta. If the equation remains unchanged, then we know for sure it's symmetrical with that polar axis. But again, that sine is a odd function. So I know that sine of negative theta is equal to negative sine theta. So that to me is going to change it. So this test does not tell me that's symmetrical with the polar axis. Now let's plug in theta minus pi. If we do that, we would get r is equal to 2 sine of 3 times the quantity theta minus pi. Actually, it was pi minus theta. So I have a difference of 2 angles, and I can rewrite my sine function using the formula of the difference of 2 angles for sine. I would get 2 sine of 3 pi times cosine of 3 theta minus sine of 3 theta cosine of 3 pi. So 3 pi, if I did that angle, that gets me to the negative y-axis. I know sine of 3 pi, that would be give me 0. And we need the bracket in front of this whole thing. So that would give me 2 times 0 is 0. Sine of 3 theta, cosine of 3 pi, that's negative 1. That would bring my coefficient of negative out front. So that would make that a plus sine of 3 theta. So this would give me 2. So that's positive sine of 3 theta, which is the same equation that we started with. And so we can see that this is symmetrical. To theta equals pi halves. So to test to see if it's symmetrical across the pole, we would plug in negative r for r, and I can see that that would change my equation. So that test doesn't work. And we can plug in theta plus pi for theta. So if we do that, we get r is equal to 2 sine of 3 times the quantity, theta plus pi. So again, we have a sum of angles for sine, 3 theta plus 3 pi. We can rewrite that using the formula for the sum of two angles for sine. So we have 2 times the quantity sine of 3 theta, cosine of 3 pi, same sign, plus sine of 3 pi, cosine of 3 theta. So simplifying this down, we get r is equal to 2. Cosine of 3 pi, that's -1. So we would have negative sine 3 theta. Sine of 3 pi is 0, so that would cancel out that last grouping. And so the r is equal to -2 sine of 3 theta, which is not what we originally had. And so this doesn't tell me if it's symmetrical with the pole or not. So we just see that it's symmetrical across the line pi halves. And so we're going to plot some points. So any point r theta on the graph, r pi minus theta is also on the graph. So let's start plugging in some values for theta. So let's say when theta is 0, we get r is equal to 2 times sine of 0, which is 0. So we have a point on our pole. Let's think about putting in points that we would know. So if I have 3 theta is equal to thirds. And so if I divide, that would be pi 6. So let's look at that, pi 6, which is 30 degrees. So 30 degrees times 3. Now it's going to actually give me pi halves when I plug it in. Sine of pi halves is 1. So I would have 2 times 1, which is 2. Pi minus pi 6. So that's 5 pi 6. I also have 2. So if we plug in pi thirds, 3 times pi thirds pi, sine of pi is 0. So pi thirds, pi minus pi thirds, that's 5 pi thirds is also 0. What about pi over 18? Because if we plug that in, we have 3 pi over 18. That's the same thing as pi 6. Pi 6, sine of pi 6 is 1/2. So 2 times 1/2 would give us 1. If I do pi minus pi 18ths, that's 17 pi 18ths. Would also give me back 1. So let's convert that pi over 18 into degrees. So recall we would multiply that by 180 over pi. And let's get what that would be in degrees. Which is approximately, or it's equal to 10 degrees. So 10 degrees, pi or 180 minus 10, that's 170 degrees. Thinking to myself, so what other ones would we know if we plug it in there? If we did pi ninths, if I plug in pi ninths, multiply that by 3, that would give me pi thirds. So sine of pi thirds is √3/2, and I'd have 2 times √3/2, which is √3, which is approximately 1.7. So R is 1.7, pi minus pi ninths, that would give me 8 pi ninths. So let's figure out what pi ninths is in terms of degrees. So pi ninths times 180/pi, the pi's cancel, 9 goes into 180, that's 20 degrees. So 8 pi ninths, that would give me 160 degrees. So let's look at, I already did pi 6. What about pi? So let's do, that's pi. Let's see what we have so far with our points. So at 0, we have 0. At pi 6, 30 degrees, we have 2. And at 2, 5 pi 6, we also have a point. At 0, so we have pi thirds. Pi thirds is back to 0. Pi thirds is 60 degrees, it's back to 0. At 10 degrees, we said we had 1. So estimate about 10 degrees, we have 1. Over here, we also have 1. At 20 degrees, we had 1.7. So that's about right here. So it's going to happen. We have something that looks like this. Did I do something? Let's do the pi fourths. So that would be pi 12ths. Because 3 times pi 12ths is pi fourths. That's √2/2 times 2. That's just √2. √2 is 1.4. And so symmetrical R is 1.4. That would be 11 pi 12ths. And so 180 divided by 12, that's 15. So that's about 15 degrees. And that doesn't help me. $5 degrees. Just that. I know it's what it's supposed to look like. It's just getting it there. Okay, so let's plot some more points. So what if we had theta was 180 degrees? When we plug that in, it's going to give me 240. Not 240, I don't know why I said 240. I want 3 theta. Let's think about this. I want 3 theta to equal 60 degrees. So if I divide by 3, what theta equal 20 degrees? We got that one. If I want 3 theta, let's say, to equal 120 degrees. So things that I know, divide by 3, then theta is equal to 40 degrees. Okay, let's look at that. So theta equal to 40 degrees. That's 120 degrees. Sine of 120 degrees, that would be root 3 over 2. Root 3 over 2 times the 2 in front is root 3, which is 1.7. There we go. 180 minus 40 degrees, that is 180 minus, that's 140, which is also 1.7. Okay, so at 40 degrees, we get back to 1.7. And then at 140 degrees, we also have 1.7. Yeah. 160, 7. So it ends up looking like this. We want to come down in here. So let's think about this too. So if I wanted to have 3 theta equal 270 degrees, I would choose theta to equal 90 degrees. So if we plug in 90 degrees, I get 270 degrees. Sine of 270 is -1. -1 times 2 is -2. 180 minus 90 is 90. Okay, so at 90 degrees, I have -2, which is going to reflect here downwards, which is here. Let's look at 240. So I'm wanting theta to equal 240, or 3 theta to equal 240 degrees. That would mean that theta is equal to 80 degrees. If we plug in 80 degrees, that would be sine of 240. Sine of 240, reference angle is 60 degrees, third quadrant. That's root 3 over 2, so negative root 3 over 2. So that would be negative root 3 is 1.7, so negative 1.7. So 80 degrees, I'd go rotate 80 degrees, but then I'm going to go across to my pole. And so that would give me negative 1.7. Which is here. 180 minus 80, that would be 100 degrees. And I would also get back, so 100 degrees times 3, that's 300. Sine is negative in that fourth quadrant, so this is again negative 1.7. So 100 degrees, we'd go over 100 degrees, and then across the pole, we'd get 1.7. And so here's our 3 petal rows by plotting those points. And so again, we can check this on Desmos. So if I pull up Desmos, we have the following picture, which is what we got in ours. So that are roses with end petals or 2 times n petals. Depending on if n is even, it's 2 times n, and if n is odd, where n doesn't equal to 1, then it's n petals. So there's one other type that we'll see, which kind of look like propellers. And let's pull that up. So these are called Limscates or Limscates. curves. Limacskates are characterized by the equation of the form r squared equals a squared sine 2 theta, or r squared is equal to a squared cosine 2 theta, where a can't be equal to 0. And the graphs are going to have a propeller shape. So let's look at graphing one of these, and then we will be finished with this section. And we'll review what we had just gone over and the different types of equations and the different types of shapes that you would get. So our next equation is r squared equals sine 2 theta. So this is going to give me a propeller shaped curve. So we can test for symmetry again. And so if it's symmetrical with a polar axis, I would plug in negative theta for theta. That's going to change my equation to r squared equals negative sine 2 theta. So it's not symmetrical with the polar axis. If we plug in pi minus theta, we're testing to see if it's symmetrical across the line, theta equals pi halves. So I have sine of 2 pi minus 2 theta. So I have a difference of 2 angles for sine. So let's rewrite this. This is sine of 2 pi, cosine of 2 theta, sine, so it's the same sign, minus sine of 2 theta, cosine of 2 pi. Sine of 2 pi is 0, so 0 times cosine of 2 theta is 0. So we get r squared is equal to, cosine of 2 pi is positive 1, so 1 times negative sine of 2 theta is negative sine of 2 theta. So this is changed. It's not the original equation, so this does not tell me that it's symmetrical across the line theta equals pi halves, but it's possible that it is. Now, if we plug in negative r for r, I can see that it's going to be changed or unchanged because I'm taking negative r and I'm squaring that value. So r squared is equal to sine of 2 theta, which is the original function. So this tells me that it's symmetrical with a pole. So let's plug in some points. So if we plug in 0, sine of 0 is 0. If we plug in 15 degrees, 15 degrees, that's sine of 30 degrees, which is 1/2. So I get r squared equals 1/2, or r is equal to the square root of 1/2. Square root of 1/2 is root 2 over 2. Root 2 over 2, I believe was that 0.7, but let me just check it again. Yeah, so plus or minus 0.7. If I plug in (30 degrees), 2 times 30 degrees is 60 degrees. That's root 3 over 2, square root of root 3 over 2. That's about 9.3. if we plug in 45 degrees, 2 times 45 degrees is 90 degrees. Sine of 90 degrees is 1. Okay, so let's see what we have so far. So at 0, we have 0. At about 15 degrees, we have 0.7. That's bigger. Symmetrical with a pole, so that basically is changing my signs. Right here. At 30 degrees. At 30 degrees, we have 9, did I say 9.3? Something off there. 30 degrees at 60 degrees, 60 degrees. Sine of 60 degrees is √3/2. Oh, that's okay. I'm sorry, that was 0.93. So almost 1. .45 degrees, we have 1. Something that looks like this when we graph it. And so let me pull that up on Desmos to show you that we would get the same thing. Okay, so when I plugged it into Desmos, they didn't like r squared equals. So we can solve for r by taking the square root of both sides. And if we do that, you'll see that you get what we got, this propeller shape that goes through the polar axis. So r equals square root of sine 2 theta. If I put that negative in front, we get the same exact thing. So that plus or minus doesn't affect anything. Okay, so let's look at the last thing in this section, which is kind of just a review of what we've gone through so far with this section in our textbook. And in our textbook, this is section 10.2. So the following states, the equations of some lines and circles in polar coordinates and their corresponding equations in rectangular coordinates are given in the table below. Also included are the names and graphs of a few of the more frequently encountered polar equations. So we talked about getting lines, and if we had lines, we would have them in the form. So a line passing through the pole, making an angle of alpha with a polar axis would be y equals tangent alpha of x. And the graph is here below where theta is equal to alpha. And that's what the form would be, theta equals alpha. If we had our cosine theta equals a, then we had a vertical line x equals a. If we had a horizontal line and rectangular equation y equals b, it would be in the form of r sine theta equals b and polar form. We talked about the circles. If we have R equals A is greater than 0, then our rectangular equation is x squared plus y squared equals a squared, where a is bigger than 0, and we had a circle centered at the origin with radius a. If we had a polar form in the form, and I said r equals plus or minus a cosine theta, then we're going to have the equation in rectangular form, where our center was at a divided by 2, 0, and our radius was a over 2, absolute value. If it was in the form where we had r is equal to plus or minus a sine theta, where a was greater than 0, we talked about it being the point 0, a divided by 2 is our center, and the radius is the absolute value of a divided by 2. Then we looked at cardioids. If you had a cardioid, it was in the form for polar coordinates, r is equal to a plus or minus a cosine theta, where a is greater than 0, or r is equal to a plus or minus a sine theta, where a is greater than 0. If it was a limacon without an inner loop, then you had r is equal to a plus or minus b cosine theta, or r equals a plus or minus b sine theta, where our value of a was bigger than b, which was bigger than 0. If we had a limacon with an inner loop, then we have r is equal to b plus or minus b cosine theta, r is equal to a plus or minus b sine theta. In this case, our b value was greater than a, which was greater than 0. We saw that we had a Limacate curve. In polar form, it was r squared is equal to a squared cosine 2 theta, or r squared is equal to a squared sine 2 theta, where a could not equal 0. If we had a rose with 3 petals, we have r is equal to a sine 3 theta, a greater than 0, or r is equal to a cosine theta, where a is greater than 0. With 4 petals, we have r is equal to a sine 2 theta, a greater than 0, or r is equal to a cosine 2 theta, where a is greater than 0. So these polar equations gives us some pretty cool looking shapes of graphs. So that is the rest of our section 10.2 in our textbook.